Thank you for attending today. My name is Neil Carpenter. I'm a Senior Escalation Engineer with the CSS Security Team at Microsoft. What we want to talk about is SQL injection, and some of this we're going to go through some code, but don't worry if you're not somebody who codes and you don't understand it. It's reasonably clear, and it's going to illustrate how things work and how this happens. So what I want to go through, I want to talk about some SQL basics at a very high level, what SQL is and what it does, which is important because it's going to illuminate the rest of what we talk about. And then I want to talk about SQL injection, what it is. It's certainly one of the most prevalent attacks we see against web servers and against web properties. But talk about in some more detail what SQL injection is and how it works. And then we're going to do some examples of those things. Talk about some other approaches to SQL injection, including automated SQL injection, which is what we've seen as the primary threat in SQL injection over the last 3 or 4 years. And then at the end, I want to talk about how to solve SQL injection, especially, excuse me, how not to solve SQL injection. So SQL is a database, which is, I guess, kind of obvious, but what SQL does for us is it stores tables of information. So for instance, in the slide there, you can see a table with usernames and passwords. This is not how I would recommend storing passwords, but it's going to illustrate some of the things we do here. So a table has columns, there's a name column and a password column, and it has rows. There's a Bob row, a Sue row, etc. And so SQL is a collection of these tables of information, and then some other things like views of the information and stored procedures that allow you to do programmatic things against the information. And then there's what's called T-SQL, which is the language we use to interact with SQL. So I have 2 sample queries here. The first one, select asterisk from users, where name equals Bob and password equals password1. What select does is it goes and gets records out of SQL and returns them to you. So in this case, what we're saying is we want to go to the table named users, find a record find a row where the name is Bob and the password is password1. The second query we see there is an insert. So we're going to add values. We're going to add a row into our table. So in the users table, we're going to add a user named Jim, whose password is password3. And that's, for the purposes of SQL injection, really all we need to know about SQL. So having said that, what is SQL injection? Very important piece. A lot of misconceptions around SQL injection. SQL injection is not a vulnerability in SQL. It's not a vulnerability in IIS. It's not a vulnerability in the base operating system. It's not a vulnerability in any of those layers that make up the platform. What SQL injection is, it's a vulnerability in the code running on top of all of that. And it really doesn't matter what kind of code you're running. You could be running ASP.NET on top of SQL 2012 and IIS 7. You could be running Java server pages on top of Apache using MySQL. It doesn't matter what the platform you're running on. SQL injection takes advantage of errors in the code you're using. In the code you're running on your web server. So, and that can be code that you have written, code that the customer's written, or it can be code that makes up a platform that you're running on top of. And I'm going to use WordPress as an example. Not that I'm aware of any current vulnerabilities in WordPress, but if you're running a platform on top of all that stuff like WordPress that provides additional functionality, that platform can have vulnerabilities in it as well. So what does SQL injection do? It takes advantage of a failure in the application to check input from a user, and that input actually contains T-SQL in it, the code, the language we use to interact with SQL. So it can it can allow an attacker to bypass authentication. That's one of the examples we're going to look at specifically. It can leak data. So if you have a database exposed to the internet that has personal identifying information or other information that's critical, an attacker may be able to use a SQL injection vulnerability to get access to that information and take it off of your SQL server. And it can also be used to change or delete existing data. Changing the existing data is what we commonly see in the automated SQL injection attacks we'll talk about later. So let's take a look at an example, or let's first talk about. There's two approaches that we're going to take, or that an attacker is going to take to inject something into SQL. The first one's what's called a URI query string. So in a URL you have multiple parts. You have HTTP, which tells us what protocol we're using. Here you have contoso.com, which tells us the server we're connecting to. And article.aspx is the path we're connecting to. Everything after that question mark is what's called a URI query string. And it's a common way for a client to pass parameters to a server-side application. So in this example, we have article.aspx, which shows us articles that are stored in the database. And we want to see the article whose ID is number 4. So an attacker can take this, and if the code is vulnerable, use that query string to insert SQL, and we'll look at an example in a minute. But the other approach is via an HTTP post, which is what we commonly see with a form on a web page. You fill in the form data and you click the button and it posts that data back to the web server. So in a post, the parameters are in the body of the request instead of being in the URL like they are with a URI query string. So for example, we see a post here, the logon page, where the username and the password are in the body of the post. So what if from an administrative side, from an IT side, what does SQL injection look like? A few things we might see. We might see data changed. This is very common where we see scripts inserted into web pages that try to execute malicious code, so that when trusting users come to the website, they get a script run because of what was injected into the backend SQL database. We might see data missing. We might see code execution. So I mentioned stored procedures in SQL before. A stored procedure is a script that runs inside of SQL. There are a few in particular, and I mentioned XP_command shell here, that allow you to do things like, for instance, XP_command shell allows you to run any process, any application on the SQL server. So if I can run XP_command shell, I can run a command prompt, I can run a batch file, I can run a utility that dumps things out of Active Directory into a file. I can run anything on that box outside of SQL. Now XP_command shell is disabled by default, but because it's useful, a customer may have enabled it, or if an attacker has sufficient access, they could enable that stored procedure as well. But the scariest thing is depending on what the attacker is after and able to get to, there may be no symptoms. If all an attacker does is log in when they shouldn't be able to log in, or get access to data that they shouldn't be able to get access to, there may be no symptoms. There may be no indication that SQL injection has happened. So how do we find SQL injection? IIS logs are the primary approach to this. The problem is IIS logs are only useful if it happened via a URI query string. So going back to these two approaches. In IIS logs, the URI query string is going to be logged. So it's a separate field in the IIS log, and you can, if you're looking for SQL injection, you can start filtering those URI query strings looking for common T-SQL commands. And we'll take a look at what that looks like a little later. But if it happens in an HTTP post, because the posted data can be of almost any size, that's not logged to the IIS log, because you could be posting a whole file. You could be posting 100K of data. So none of that gets logged to the IIS log. If SQL injection is happening via HTTP posts, your only clue is going to be maybe looking at, in the IIS logs, there's client server bytes, CS bytes, and server client bytes, SC bytes, which represent the amount of data passed from the client to the server and from the server back to the client. And you may be able to see variations in the normal pattern there. If a post request is usually 150 bytes and it usually returns 2K, and then you get one that's 1,000 bytes and it returns 20K of data, that's going to stand out. But it's not conclusive. Fortunately, most of the SQL injection issues I've worked with happen via URI query strings. So generally speaking, that's where we're going to find it. So background, let's take a look at what this actually looks like. And this is an extremely poorly coded app. I'm going to say that right up front. I coded it poorly so that we could use it as an example. This is not how you should write your login page, but it's how I've seen login pages written. So what we have here is we start by making a connection to the SQL server. So we have a connection string that specifies the server and how we're going to log in and what our default database is. So we make that connection, and then we build a query so that we're back to T-SQL. And what we see here is we're going to select any records from the users table where the name equals, and this is what's called string concatenation. So we have a variable called user that's coming off the URI query string, and we're going to insert that into here. And the password equals the password from the URI query string. So whatever the user puts in for username and password get inserted into this query. And then we create a SQL command, we execute it, and then we check to see if there's one or more rows in the results. And the assumption is if your username and password were in the users table, then making this query is going to return one result for whoever you logged in as. And so obviously you're a legitimate user because you know a username and the associated password, and everything's okay. If it returns 0 rows, it means you're not a legitimate user. You got the password wrong, you don't have a username, and so everything fails. So let's take a look at what this looks like. Share my primary monitor here, and you're going to see IE looking at this. So we're going to log in as Bob, and we know that Bob's password is password1. And we click login, and we see that our login was successful. Now let's try logging in as Joe, who doesn't exist in our users table, and we're going to put in password for Joe. And you can see I've already tested this. And you see Joe's login failed. But let's construct this a little differently. So what I've done now is I've put in SQL injection, a SQL injection string. So now the full query is going to read select asterisk from users where user equals Joe and password equals password1. And then the apostrophe breaks that, or ends that part of the where clause, and we add on or 1 equals 1. So 1 always equals 1. So that's going to make our query return all results because 1 will always equal 1. On the tail end of this, there's a semicolon, which marks the end of a SQL command, and then the dash dash tells SQL that anything after it is a comment, which just prevents anything else that's added to that query from actually affecting our injected string. So we click logon, and you'll see even though Joe doesn't exist, our logon was successful. So that's kind of a basic example, but this is how, for a vulnerable application, you could use SQL injection to bypass authentication in the application. So let me jump back to the PowerPoint slide here, and let's jump back and take a look at what happened here. So once again, this was the string mySelect query. So we select asterisk from users where name equals, and the user variable was Joe, so Joe gets inserted into there. And the password equals, and that was equal to password1 apostrophe or 1 equals 1 semicolon dash dash. So when SQL executes that, it doesn't know that the rest of that is not supposed to be part of that statement, that the or 1 equals 1 isn't supposed to be part of the select statement. So it says, well, in the users table, there's no user named Joe and password equals password1. But the or part, 1 equals 1, is always true, so it's going to return all the users in that table. Because our results, our rows returned, we assume that Joe's a valid user, and on we go. So that's kind of a basic example. Let's move forward a little bit and take a look at another example of really poorly written code to provide an example here. This is code that returns articles stored in a database. So another common use of SQL for a website is to store some kind of content in the database. At a very high level example, SharePoint stores almost all the content in a SharePoint portal in SQL. So when it renders the web page, it's pulling content out. This is a slightly simpler example. This would be a website where they say there are news articles that show up on the front page, and you can click on an article to read that article. So in the database, each article has an article ID, and each article we can click on the article and pull it up. And what happens is that we add that to the URI query string. So the query string is article.as, or the URL is article.aspx ID equals and some article number. So we can see in the code here, same thing. We create a SQL connection. We build our query, select the body of the article from the articles table where the ID is equal to the article number. And we create a command, open the connection, execute that command, and we return the body of the article back to be displayed on the web page. So let's take a look at what that looks like as well. Let me share my desktop again. So as this is coming up, you can see that I've brought up article number 4. It's the common lorem ipsum article, which is default text used to fill in anything. So that's all well and good, but let's do something else here. So let me actually copy out what I've got here, and I'm going to bring up a whiteboard for a minute so that we can take a look at what we're doing. So there's what my whiteboard disappeared on me. Try that. There's what I've put in there. And so what we have is the same thing we saw before. Is we have the legitimate part of, in this case, our URL, ID equals 4, and the semicolon, or I'm sorry, not the apostrophe to mark the end of that. Now I've put in a semicolon, which once again separates different T-SQL statements, and this time I've put in a separate statement. And what I've put in here is update, which means we're gonna change text that exists already in the database. So I'm going to update the articles table. This %20 is a space. I have to escape it as %20 because URLs can't contain spaces. But when this executes on the remote side, that %20 is going to turn into a space. So I'm going to update the articles table. I'm going to set the body of the article equal to the string new text, where the article ID equals 4. So I'm going to change article 4. Instead of reading lorem ipsum doros, etc., it's just going to read new text. So let's go back over to Internet Explorer, and we'll execute that, and you'll see now article 4 instead of lorem ipsum comes up as new text. And even if I go back and just refresh that, there it is. So we've actually changed that in the database. We've made a change in the database just from the URL. Now obviously that's a fairly simple script. When we look at the automated examples, there are much more complicated scripts. We'll break down one of those in a minute. But that gives you an idea of how SQL injection works and how a vulnerability in an application can be exploited. Those were fairly simple examples, but they get much more complicated. So one other thing that happens is called blind SQL injection. This is a way that attackers can map out a database and understand things about it, even if they can't return data directly from it. So they'll build queries that do things like test to see if an error gets returned on the query. And if an error gets returned, that tells you one thing. If an error doesn't get returned, it tells you that your query was actually well formed, executed, and that you can do more with it. And then you can build more queries and keep mapping out the database. You can do things like test for the names of various tables and then test for the columns in those tables, and then see if particular information exists. There are tools for automating this, but blind SQL injection is something we would usually see in an attack targeted specifically against a particular application. It's not that common. What is common is automated SQL injection. So prior to 2008, SQL injection was something in our casework we saw very rarely. Because it requires a lot of work for an attacker to find a site that's vulnerable to SQL injection and then sit down and figure out, what does the database look like? What tables are there? What can I do with those? What columns are in those tables? How can I get data back? How can I use this to my advantage? It's a lot of work and it requires a high level of skill. But in 2008, what we saw was a series of SQL injection attacks that continue through to today that have been automated. And instead of requiring a lot of skill to compromise a single site, now literally millions of sites have been compromised over the last 4 years by tools that simply go out to Google or Bing, or well, the tool I've seen a copy of went out to Google, and it searched for websites that met a particular set of criteria that looked like sites that might be vulnerable to SQL injection, and then it went through them one at a time and just ran a script against them. And those that were vulnerable were defaced so that when legitimate users came to their site, there were scripts embedded in the text that was returned. Now, it started with ASP, so the original tool would go look for ASP sites where there were URLs in Google that included a question mark indicating that it took URI query strings. After that, we saw it move on to other platforms, ASP.NET, PHP, Cold Fusion. Pretty much every web platform we've seen this effect. And it's slowed down, but it continues to affect new sites or vulnerable sites or sites on platforms that they're just now getting around to testing against. It may be a platform that's made a change. So I saw an instance recently in which the customer's website had been using a flat file rather than a database for everything that was backing the website. And so they upgraded and moved to using SQL to back the website, and almost as soon as they did that, because their code was poorly formed, the site was defaced by an automated SQL injection attack. So what does this look like? Well, this is what we found in the IIS log, and I've edited some of this out. You'll see that there's a long hex right after cast in there. There's a long hex number. That number actually goes on for quite a while. I just put 3 dots in there because it wasn't helpful to cover the whole slide with hex numbers, really. But this is what we saw, and this is a very interesting injection. So you can see once again the URI query string there, ID equals Z, and then a semicolon, and then a SQL or several SQL commands in a row. And you can see a 200 OK further down, which indicates that executed OK. It took 17,000 milliseconds or 17 seconds to actually execute. So let's take a look let's break this down into what it actually means. So the first thing in there are 4 SQL commands in there. The first one is declare, which sets a variable. The variable name is S. It declares it as nvarchar, which is a type of string, just text characters. The next thing is it sets S. I'm sorry, there are 3 SQL commands here. One of them wraps around on the second line. It sets the variable S, and it casts that long hex string as a string. So what this is doing is it's taking that hex string, which is you can tell it's in Unicode because it's every other character is 00, so 45, 43, 4 is an 8-bit character set expressed in Unicode. So it takes that hex number and turns it into text. And then the last thing it does is executes the contents of the variable S as though it was a T-SQL script. So that long hex string, what does that break out into? Once we convert it from hex into text, here's what we get. And this is a very clever script. What the script does, starting at the top, it declares a few variables, and then it uses a cursor, which allows it to move from place to place. And what it does is it goes through, there are a couple of system tables inside of SQL. Sys-objects, sys-columns are the 2 that are used here, which tell us the tables and the columns in that database. So it's a table of tables and a table of columns and tables. And it goes and looks for columns that you'll see b.xtype equals 99, equals 35, equals 231, equals 167. Well, these x types are string types, so these are like varchar, nvarchar. It's looking for any table anywhere in this database that has columns that are of a text type. Because what it wants to do is, as we go down a little further, you see it executes another piece of script. And that script is an update statement, like we looked at earlier when we changed the contents of article number 4. In this case, what it does is it goes in to each row in each column that has a text type, and it appends a script tag to that. And that tag pointed to a script hosted on 211.796 something.net out on the internet that tried to take advantage of various client-side vulnerabilities. So it inserts that into every piece of text in the back-end database that it can get to. And then it closes it and deallocates it, and it's done. So now what we've got is a piece of script that goes through, and I keep repeating this, but it really is very impressive in terms of the approach. Every bit of text that you've stored in SQL for your website now has this script tag embedded in it. So now, like in our example with article.aspx, now when we pull up an article, at the end of that article is a script tag. And now when my browser interprets that, it goes out and pulls down this script and tries to execute it. And if I have client-side vulnerabilities, I end up with malware on my client, which is very impressive because I may be a website you trust. I may be your chess club's website. And so now when you go to see when your next game is, the website you trust is attacking you with this script. So when we get to the end of this, the question from a customer really is, how do I fix this? And the hard answer is, well, so first of all, you're going to have to fix your database. In some cases, it's possible to script that, but what we've seen is there are cases where appending that script tag to the end of or inside of that text column may cause what's in that column to be longer than, or what's in that row to be longer than what that variable is defined as, so things can get truncated and you can lose things. The best option is to restore from a known good backup of the database. If that's not possible, if you're good with SQL, it is possible, since you know the string that was inserted, to use essentially very similar to the code that they had there, but to go through and remove it instead of adding it. But once that's done, the only way to really fix this is to fix the code for the website, which is very difficult for the customers that I work with. And the reason it's difficult for the customers I work with is usually I'm not working with the developer. I'm working with the IT pro who manages that website. The developer might work for the same company. It might be somebody they contracted a couple of years ago to write an application. It may be difficult to get a hold of that person. That person clearly wrote bugs into the existing code, so there's an open question if you're that IT pro of whether you trust that guy to fix the same code. But that's the only way you can resolve this in the long term. No matter what else you do, that application remains vulnerable until you fix it. That's a hard message. So there are some things we can do that help to mitigate this in the short term. There's something called URL scan. What URL scan is it's a plugin for IIS. It runs on top of IIS, and it allows you to create rules to block certain things incoming. So what you see here is a suggestion for using URL scan to block SQL injection. And on the left, there's how you would set it up. So it applies to ASP and ASPX pages. This may differ if you're hosting Cold Fusion or PHP or whatever else. You're going to deny, you're going to scan query strings, and you're going to deny based on that. And on the right-hand side is a list of suggested strings to search for. Now the problem with this is, first of all, I always joke that as IT security pros, we have to be right all the time. The guys attacking us only have to be right once. And it turns out when the automated SQL injection attacks started, we revised URL scan to scan URI query strings. It didn't used to. Prior to 2008, it didn't scan query strings. But we released a new version that did that. And a couple of months later, what we saw was that attackers were able to construct an attack in such a way that it got around the changes we'd made to URL scan, and we had to release a second version of it to fix that. But the other problem here is you're scanning for a bunch of text. Some of that text may be legitimate. So for instance, if you were running a web front end for, say, a medical supply store, somebody might want to order a cast to put on their arm or their leg or some broken bones. So blocking cast is going to be very bad because now you've interrupted your legitimate business. This is really a short-term mitigation that allows them to block an ongoing attack while figuring out how to fix the code. Now that's URL scan. IIS 7 and later has the same, essentially the same functionality built in. It's called request filtering. It can do the same thing. You see an example here of setting it up. And once again, it applies to ASP or ASPX. If you were using a different platform, you would want to change that, and you add a set of strings that you want to deny. Same problems, that an attacker may find a way around the strings that you've added, and on the other hand, you may be blocking things that are legitimate for your website. So these things are short term. A customer can use them to get back to business, prevent it from happening, and buy themselves some time to fix their problem. But what they have to do is fix their problem. So now this is where it gets interesting. A lot of people have written a lot about fixing SQL injection problems in code. And it turns out that in terms of the security development lifecycle, the SDL, what Microsoft uses and recommends as an approach to writing secure software, a lot of what's been written about fixing SQL injection is just wrong. Which is not to say it won't work sometimes, but it's kind of like using URL scan. It's not a perfect solution, so you may fix the problem and break something else, or you may only partially fix the problem and have an attacker who finds a way around it. The thing that you hear most often is you have to sanitize your input. You have to take what the users provide and search it for apostrophes and double dashes and semicolons and replace those and do things like that with them. So, once again, first of all, it's not fixing the problem. You're just working around it. Above and beyond that, it's back to we have to be right every time. The attacker only has to find out one way around that to beat it. So what's the actual solution? The actual solution in the SDL, there are three things. This first one is the biggest. It's to use something called parameterized queries. So instead, in my bad sample code, we were concatenating the query. We were just creating a string and adding in what the user passed us for the username and adding in what the user passed us for the password and executing it. Instead of doing that, when you parameterize a query, it looks like this. Select asterisk from users where user equals @u and password equals @p. Probably if you were writing really good code, you'd use something better than @u because it's not a very descriptive variable. But it fits in the slide. So what this does is you separately add the parameters to the query. So you can see that I use C# down below, command.parameters.add with value, and I set the @u parameter to be whatever the end user passed in for the user string. So this is very cool because what happens now is when SQL executes this command, it knows what is the actual command and what's the data in the command. So if I've inserted password1 apostrophe or 1 equals 1 semicolon dash dash, now SQL tries that whole string as the password. And it fails because that's obviously not the right password. It doesn't execute the or 1 equals 1 part, and so it never works. Same thing with our update statement. It would just assume that the ID for that article was 4 semicolon update, etc. And when it queries for that, it's going to return 0 results, and your article is not going to display, and that's going to be it. This is the single best way to solve a SQL injection vulnerability. It's effective, and it solves the problem. It prevents code that the users put into a field or somewhere else from executing. This is the #1 recommendation in the SDL. The #2 recommendation, we mentioned stored procedures earlier. Stored procedure is just a script. It's a piece of business logic that executes on the SQL server. So you can take those parameterized queries a step further and put that whole query logic inside a stored procedure. So instead of saying select asterisk from users where user equals something and password equals something else, you can have a stored procedure that's called authenticate user, and it takes a username and a password as parameters. And now you've reduced the attack surface even further. So now there's not even it's all abstracted on the server side. Of course, you have to properly create the stored procedure. If the stored procedure does the same concatenation stuff where it just takes the input and adds it into a query and executes it, the same thing's broken, but this helps. And the third thing is, sorry, go back one here. The third thing is that above and beyond that, you can affect your permission. So you grant the permission so that the web user, the application, the user the application connects as, is only allowed to execute stored procedures. They're not allowed to access the data in the tables or the views directly. So now there's even less scope, because the only thing they can do is execute that stored procedure that checks the username and password and returns a yes or a no. They can only execute the stored procedure that takes an article ID and returns the article. They have no direct access to the tables in SQL. So that's an overview of SQL injection from start to finish, what it is and how it works and the best way to solve it. So with all that out of the way, are there any questions?
Hey Neil, yeah, I have a question regarding the parameterized queries.
Sure.
So could you go a couple of slides back? Yeah.
Yep.
So when we use this the cmd.parameters add with value, so do we do a user input validation here, or we just gather the information here?
Depending on what you wanted to do, you could certainly validate the input further, but it's not really necessary. And it's not for this. I mean, there may be other reasons that you need to validate that input. But in terms of making a query with SQL, what this does, like I said, it separates out that the select statement above that is the executable code, and SQL knows that's executable. And it knows anything in the @u variable is just data and not to execute it.
Exactly.
So the only point, I'll tell you the only point where validation would be important here is what people call second-order SQL injection problems, which is where you can write data into a table and then display it back later. And in that case, you could still insert things into, like if you were storing, like say I had a web page that allowed me to edit the articles on the website, and I type in an article, I might want to validate what's in that before I store it in the database, to prevent a malicious user from inserting malicious things into that article that gets displayed back to end users.
Okay. So it's more of a data that rather than any query that is being, or a piece of code that is running in the password or the username field.
Yes.
Yeah.
So other questions? Was this? I know this is kind of a lot of information stuffed into a relatively short period of time.
This definitely was very informative, Neil. We'll start to make sense once we work on similar issues. Yeah, but the thing is, like I was aware about the parameterized queries, and but I didn't know how do we implement it exactly.
Yep, and this is, I showed an example here with C#, but every web platform that I've looked at implements a similar procedure. It may be different, but I've looked at it in Cold Fusion and in PHP and in ASP and in ASP.NET, and every platform I've looked at has a similar concept. It's just a matter of how they accomplish it.
Okay.
So if the customer is using Cold Fusion, then we may have to say, well, you got to go talk to Adobe to figure out how to do this, but that's what you need to do. The concept is the same no matter what language or platform they're developing on.
Sure. So this slide would be available, and the recording as well, right?
The recording will be available, yeah. So everybody knows we started doing this brown bag series on incident response topics a few months ago, and this is actually the first presentation we did, but we had a problem with the recording of it, so I wanted to present it again so I could record it and get it right. So I appreciate you guys joining me. But each of these, there's going to be one of these a month. Each one will be recorded, and I'll have to dig up. I don't have the information on where the recording is. Angela and Larry Gandy do all that work. I just show up and present topics sometimes. But all of them will be available on CorpNet. So we've done SQL injection. We did we did one on pass the hash attacks. This month we did one on targeted attacks against customers and mitigations that specifically help prevent targeted attacks.